Hi Year 11, this is our fifth lesson for the topic of functions. In this lesson we're going to look at non-linear relations. So we are getting closer to finishing this topic off. It has been a long topic. So far we've covered functions and function notation, linear relationships including direct variation, and quadratic functions. And in this lesson we're going to look at absolute value graphs, hyperbolas, inverse variation, and circles and semicircles. So let's start with absolute value graphs. The graph of an absolute value linear function has a V shape, like this. And the reason is because the absolute value strips the negative off. It's okay when we put in 0, 1, 2, and 3, we're going to get 0, 1, 2, and 3 in this case. But when we put in -1, -2, -3, we strip the negative off and we get 1, 2, 3. So instead of the line continuing down here, it's going to bounce up. So that's how we end up with the V shape. Now, like any graph, we can transform it. We can add a number to the end. That's going to take our basic graph and move it up to. We can also shift it sideways. So this is a horizontal translation. It's going to take this graph here and move it over to what makes 0, which is x is equal to 1. So it's going to move it over to here, like that. We can also dilate it by changing the coefficient of x. So this is going to make the graph steeper. If we had a fraction here, like a half, that would make it flatter. Now we've already spent some time solving equations that involve absolute values algebraically. But how do we solve something like this graphically? What we're going to do is graph the left-hand side of the equation and the right-hand side of the equation and then find the points of intersection. So let's have a look at this. We want to graph y equals the absolute value of 2x minus 1. So it's going to be a V graph. And to find where it bounces, we just solve 2x minus 1 equals 0. It's going to bounce at what makes 0, which is going to be a half. This 2 is going to make it steeper than normal. So here's our graph. Y is equal to the absolute value of 2x minus 1. It's bouncing at a half, and it's steeper than y is equal to x. And here's the graph of y is equal to 2. It's a horizontal line. Now the points of intersection are negative 0.5 and 2, and 1.5 and 2. But when we're solving an equation, we actually only want the x values. So the solutions are x is equal to negative 0.5 and 1.5. Let's move on to hyperbolas. A rectangular hyperbola has a general equation y is equal to k over x. And look at how that is different to the other functions that we've looked at. It's got an x on the denominator. It creates this funny looking thing. It's also called a reciprocal function because this is turned upside down. Now a hyperbola will have two asymptotes, a vertical one and a horizontal one. Remember, an asymptote is a straight line that a curve approaches but never cuts it or touches it. So this gets closer and closer and closer. And when we want to show asymptotes on a graph, we draw them as dashed lines. Let's have a look at how we sketch a hyperbola. We start by finding the two asymptotes, and we start with the vertical asymptote because it's the easiest. If we want to find the vertical asymptote, we look at the denominator because this cannot be equal to 0. We can't divide by 0. So x minus 1 can't equal 0. X can't equal 1. That's our vertical asymptote. And then when we draw it up, we're going to draw a dotted line through x is equal to 1. Next, we want to find the horizontal asymptote, and it's a bit trickier, but the easiest way to do it is just to switch the x minus 1 and the y. Switch them around. We get x minus 1 is equal to 1 on y. What can't y equal? Have a look at the denominator. 0. So there's our horizontal asymptote, y equals 0, and put it in with a dotted line. Next, we look at whether this is a positive hyperbola or a negative hyperbola, and we're looking at the coefficient of x. This is positive, which means that we're going to be in the positive quadrant. So part of the hyperbola is going to be up here. And then to draw the other part, which is down here, we need the y-intercept because we don't know where it's going to cut the y-axis. Remember, the y-intercept occurs when x equals 0. So let's substitute in x is equal to 0. That gives us 1 over negative 1, which is negative 1. So it's going to cut through here. And just drawing it in, there's our graph. Let's have a look at a harder question. State the two asymptotes for y is equal to 2 plus 1 over x minus 3. And the vertical asymptote is very easy. We're just looking for the denominator. X minus 3 can't equal 0. So x can't equal 3. That's our vertical asymptote. Now, with the horizontal asymptote, I'm going to take this 2 over the other side, like this. And then I'm going to switch y minus 2 and x minus 3. What's the horizontal asymptote? What can't y equal? Y can't equal 2. Do you see that? Otherwise I'd get 0 on the denominator. So our horizontal asymptote is y is equal to 2. Let's move on to inverse variation, which is related to hyperbolas. If two quantities vary inversely, then as one goes up, the other goes down in proportion. Or as one goes down, the other goes up in proportion. Now remember when we did direct variation, we had both of the quantities going in the same direction. As one goes up, the other goes up. So this one's opposite directions. We write A is proportional to 1 over B. And you can see that that sort of looks like a hyperbola with the pronumeral on the denominator. But some students prefer to start straight here, and this is a little easier. A is equal to K over B. And K, remember, is the constant of proportionality. Here's example 1. The travel time varies inversely with the speed of a vehicle. Now this makes sense. The faster you go, the less time it takes. Can you see as one goes up, the other goes down? That's inverse proportion. If the vehicle travels at 60 kilometers an hour, the journey takes 45 minutes. Write an equation linking t, which is time in hours, with s, which is speed in kilometers per hour. Now I can already see a mismatch here. We've got minutes and hours. We're going to need to convert this into hours. So let's write an equation. T varies inversely with s. So t is equal to k over s. Now let's substitute in t is equal to 0.75, that's 3/4 of an hour, and s is equal to 60. Multiplying both sides by 60, k is equal to 45. What is the significance of the constant of proportionality? So let's have a look at our equation. What's the significance of this 45? Let's have a look at the distance, speed, time triangle. The triangle tells us that time is equal to distance over speed. Distance over speed. So that 45, it's the distance to be travelled. How long will the journey take if the speed is 75 kilometers per hour? So let's look at our equation. T is equal to 45 over s. S, in this case, is 75. Substitute it in, work it out on the calculator. We get 0.6, which is 0.6 hours. Now I'm going to show you a trick. On your calculator, if you use this button, which I sometimes fondly call the bubble button, it's going to convert any decimal to base 60. And of course time is base 60, isn't it? There are 60 minutes in an hour. So once you've got 0.6, just press that button and it's going to give you this, which means 0 hours, 36 minutes. So the journey takes 36 minutes. And D, what speed is required for the journey to take 30 minutes? Again, we need to convert this to hours, but that's easy. That's 0.5 hours. So substitute that in here. We can switch these around. So S will equal 45 divided by 0.5, which is 90 kilometers per hour. Here's example 2. A bus costs $400 to hire for an excursion. There are X children who are going to attend. Write an equation for the cost per child. Now we can see that this is an inverse proportion question. The more children there are, the less the cost per child. So we're going to start with C being the cost per child, and it's going to equal K over X. Now what is K? Well, let's think about it. If we only had one student going, it would cost the whole $400. Substituting that in, 400 is equal to K over 1. K is the total cost. It's 400. So there's our equation. C is equal to 400 over X. What is the cost per child if there are 46 children attending? C will equal 400 divided by 46. Grab my calculator. 400 divided by 46 gives me $8.70. To run the excursion, the cost needs to be below $7 each. How many children need to attend? So this time I'm going to substitute 7 for C. We can switch X and 7. Grab the calculator. 400 divided by 7 is 57.1. So how many children do I need? Is 57 okay? No, it's not. We need to round up. We need 58 students. Here's a famous puzzle. If it takes 100 people 100 hours to paint 100 houses, how long does it take one person to paint one house? Now it is a bit of a trick question, because a lot of people will look at this and go, well, just 1 hour. But that doesn't actually make any sense. It's an example of inverse variation. Now I'm not going to answer the question, so you're going to have a think about this and try and figure out what the answer is. Let's move on to our last part for this lesson, which is on circles and semicircles. A circle is not a function, it's a relation, and that's because it will fail the vertical line test. It has the general equation x minus h all squared plus y minus k all squared equals r squared. HK is the center. In other words, what makes 0 here and what makes 0 here. And r is the radius of the circle. Note, if the center is 0, 0, then the equation is just x squared plus y squared equals r squared. Here's our first example. State the center and radius of these circles. X squared plus y squared equals 25. So the center will just be 0, 0. And the radius is going to be the square root of 25, which is 5. How about this one? It's what makes 0 here and what makes 0 here. So 1, negative 3. And radius is the square root of 16, which is 4. Last one, what makes 0 here? 0. What makes 0 here? Negative 4. And in this case, we're going to do the square root of 5. And we won't work that out as a decimal, we'll leave it in exact form. Example 2. By completing the square, find the center and radius of the circle x squared plus 2x plus y squared minus 4y minus 4 equals 0. Let's start by rearranging things a bit, just to create some gaps. I've taken this minus 4 over the other side. Let's complete the square here. Find the term in x. The coefficient is 2. Halve it, square it. Half of 2 is 1, squared is 1. Whatever I do to one side, I do to the other. Locate the term in y. The coefficient is negative 4. Halve it, square it, is 4. Whatever I do to one side, I do to the other. Now let's complete the square. This is x plus 1 all squared plus y minus 2 all squared equals 9. The center is, what makes 0? -1, 2. The radius is 3. If we're asked to sketch it, here's our center, -1, 2, and the radius is 3. Now a semicircle can be a function. If we take our equation and make y the subject, let's start by taking x squared over the other side, I end up with y squared is equal to r squared take away x squared, and now take the square root of both sides. I have y is equal to plus or minus the square root of r squared take away x squared. Now this is still a full circle because of the plus minus here, and it's still a relation, not a function. But if I take either one of these, either the positive square root or the negative square root, I get the semicircles. So this one here is the positive square root, and the blue semicircle here is the negative square root. So our general positive semicircle is y is equal to the square root of r squared minus x squared, and the general negative semicircle is y is equal to negative the square root of r squared minus x squared. Now in the advanced course, we only need to worry about semicircles centered at 0, 0. Okay, that's it. Our last lesson for this topic is coming up, and it is on combined and composite functions.